Okay, we're going to pick up here with chapter 4. And as I mentioned, I think last week, hope you had a good holiday weekend. Um, chapter 3 has been posted, so hopefully you had a chance to watch it. Again, you are responsible for that. Again, because of the holiday and so forth and exams, we're going to kind of pick back up here with chapter 4. Again, if you watch chapter 3 and you do have questions on something, please feel free to ask. But again, we're not going to officially together go over chapter 3. All right. So chapter 4, which should be the last one before our first exam, dare I say, coming up at some point. It's about atoms and elements. So we're going to talk about the atom. We'll talk a little bit about some of the experiments that led to the understanding and the structure of the atom. We'll talk about in this chapter protons, electrons, neutrons. We'll talk about how you calculate how many protons, electrons, neutrons an atom has. We'll talk about the periodic table. And if that's not enough, I think we will also get into electrons, electron configuration. And if that's still not enough, then we'll talk about some periodic trends. So there's a lot bundled here into this chapter. So might as well get going on it here. So we're going to first talk about really atoms and elements. And really atoms are really the basic representation of any element you could have. Elements which are obviously on the periodic table, you could think of as really as far back as you could go in terms of a substance. You can have really just elements. You can't really go back any further. And really, the basic representation of elements are atoms of those particular elements. Remember, we talked about some other words along the way that does pop up. We talked about molecules, which is the combination of two or more atoms. We also, I think, talked about an earlier chapter as well the difference between, say, that and a compound, or what is the difference between that and a compound. A compound is the combination there of two or more atoms of different elements. So that is the key part of what makes something a compound versus, say, just a molecule. With that being said, as we'll talk about here as well, there are certain elements that, again, do come as molecules. And those were those 6 or so: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodide. And each of these, the way that they naturally come is what are referred to as a diatomic molecule. Diatomic meaning it has basically two atoms, and it's a molecule. And they are a molecule because they do basically meet the definition of a molecule, which is just simply you need two or more atoms together. So what that means is a molecule could be two or more of the same atoms of the same element, or they could be two or more of different elements coming together. But you could think of a molecule again as just a basic definition of all you have to sort of have to make it a molecule is two or more atoms basically coming together. They could be the same, they could be different, doesn't really matter. It will be considered a molecule. Now, a compound, on the other hand, as I mentioned before, you need to have two or more atoms come together, but you also need the second part of that, which is you need two or more elements also coming together for it to be a compound. So each of these guys over here on the right are molecules. They are also elements, each of these guys, and that's because they are only made up of atoms of the same element. So two hydrogens is only hydrogen atoms, so that makes it an element. Two nitrogen atoms coming together is just nitrogen, which makes it an element, but there are also molecules as well. None of those guys on the right there, H2N2O2, would be considered a compound because they only have atoms of one element. There's just hydrogen per example there and stuff like that. Now, if you had something like water, which is H2O, and again, looks something like that. This is also a molecule because, frankly, you have two or more atoms together, right? You got three of them basically coming together in this particular case. This would also be a compound because you have two or more elements or atoms of different elements coming together. This would not be an element because obviously you have hydrogen and oxygen involved there. Those are two different elements. So again, in order for something to be an element, it does has to be just that one element by itself. Outside of those kind of seven over there on the right, most elements come as monoatomic, which means they come as ones. So you had like iron by itself, it would just be Fe, nothing else with it. So most elements to come sort of as monoatomic, they come as ones. These guys are elements that come as twos, which makes them molecules, but not compounds. You can take a compound like water, for example, and you could run an electrical current over it, and you could actually break it into its elements, like hydrogen and oxygen. So you could go from a compound to elements through some type of chemical means, like a chemical reaction. But as soon as you get to the hydrogen and oxygen, you can't go any further. So that's as far back as you could go, as you could break it up. One of the things about elements, you could think of it like the alphabet, right? There's only, I don't know, 26 letters, I think, still, hopefully. And although we only have 26 letters, you used to be able to open a dictionary. I guess you just Google that nowadays. But you can open a dictionary that has a lot of different words that are made up of those 26 letters. And so sort of the same idea with elements, depending on what elements come together or how many of those elements come together, they'll be able to form different compounds and substances along the way that will have different properties. So you can think about elements as the basic building blocks of sort of compounds and things that are made. And they're, again, as far back as you could go. And again, kind of like the alphabet, there is what we use to make all kinds of different words. Now, when we write elements, we typically refer to the elements as their symbols, which is what you see on the periodic table, for example. And depending on sort of the element, you will either see a one-letter symbol or a two-letter symbol. If it is a one-letter symbol, it should always be capitalized. So if you have something like potassium, which is K, the K should always be a capital K. Any one-letter symbol should be capitalized. If it is a two-letter symbol, much like what we see with aluminum here, the first letter is capitalized, the second one is not. So those are basically kind of the rules that we follow for symbols. We use symbols obviously in naming and formulas. We use them obviously when we write equations to write proper formulas along the way for these elements. Elements are pure substances. A pure substance is pretty much what it sounds like. It is basically just one thing, right? So if you had, for example, water by itself, that is a pure substance. If you had some sand by itself, that is also a pure substance. If you had just some iron metal by itself, that is a pure substance. So any element is a pure substance. Again, even our hydrogen gas, which are two hydrogens together, also a pure substance. That's all that you have. They cannot, as I mentioned before, be broken down any further. They're, again, as pretty much as far back as you could go. And typically, if you do want to break things up into their elements, as I mentioned a second ago, you pretty much need some type of chemical reaction, chemical change to occur to do that. As you might know as well, when you do some type of physical change, for example, that is not enough to break something into its elements. A very common example is, for example, we take our water. What happens when you take water and you heat it up to make some pasta? It boils, right? And you make steam, right? That's like a physical process. Is the steam still water? Steam is still water, right? You didn't make anything new. You didn't break it apart. It's just a physical sort of change. If it was a chemical change and you broke that into hydrogen gas and oxygen gas, good luck getting to the pasta part of the evening. It's not going to happen for you. So it's going to probably explode on you. So obviously, physical changes, what we have and what we end up with are basically the same thing. It's a chemical change that what we start with and what we end with is something different. And those are usually involved chemical reactions when we talk about sort of those chemical changes. But back to the elements, obviously, in your book, you have a periodic table in pretty much a lot of places. You do need to, I'll be honest with you, you do need to have some familiarity with the name of the elements and the symbols that go with it. Obviously, it's part of this chapter here. But outside of this chapter, when we get to, I want to say 6 maybe, because we skipped 5, I think. When we start talking about nomenclature and naming things, there's lots of rules that you need to follow when you name things. So if you're still struggling, for example, to figure out, what does this symbol K represent or Na represents, you're going to have twice the hard time. So I would take some time now, especially in this chapter, which again is part of this chapter. You need to maybe get some familiarity with a good amount of sort of the names and symbols that go with it. You will be given a periodic table that only has the symbols. It does not have the names. You will need to kind of know those names. So when you look at a periodic table such as this one here or that one up on the wall, I would say definitely, as bad as it's going to sound, kind of to the left here, we deal with a lot here. To the right, we deal with a lot. Kind of up on the top area, we do not too much. The bottom 2 rows, we don't deal too much with those guys, and the last couple rows, but kind of definitely, to the left couple of rows or columns, kind of to the right and kind of top middle is where we deal with a lot of sort of those elements. So again, not too much on the bottom 2 rows there. Definitely they're by themselves, and really not too much sort of and it varies on the periodic table you're looking at as to how much is filled in kind of on this row here. Some may have more or less sort of filled in depending on where your periodic table is made. So again, the more you sort of have some familiarity with it, it definitely will help you when we get into some later chapters when we talk about naming. Now, in terms of symbols, they do come from a variety of sources. They come from historical names. They come from Greek names. They also come from where things were invented or discovered. So we get names, and also names after people as well. So, we get like francium and Berkelium and Nobelium and all those type of names that are, kind of named after people and stuff like that. Good news is those are usually like the bottom. Those are all kind of man-made elements there towards the bottom row, in a sense. So I would say, U is probably the only one maybe from the bottom there that will pop up a lot, and that's uranium. And that does pop up a lot. Definitely chlorine, iodine, magnesium, we see a lot. Not so much these guys, curium and stuff like that. We don't really see too much of that. I think we'll see a list coming up a little bit more as well. But as I mentioned before, it's really important if it is a 2-letter symbol, not to capitalize both letters. As you can see in this example, if you do capital C, lowercase o, that is an element, cobalt. If you do capital C and capital O, that is carbon monoxide, which is very different than cobalt. So if you're somebody that writes capital letters for everything, do not write capital letters for symbols for both of them. Definitely only if it's a 1-letter symbol you can do it, but don't do it for both, because you may be actually saying things you maybe do not mean. I would say in terms of some of these 1-letter symbols that we see here, these are ones we definitely come across a lot: carbon, sulfur, nitrogen, hydrogen, cobalt, silicon, neon, and helium. Again, those are definitely some that we see a lot. So as you go through this list, and again, some of the popular ones there: aluminum, I would say, barium, boron, bromium, cadmium, calcium, carbon, chlorine, chromium, cobalt. These are, again, all the ones we see. That is copper, Cu, which sometimes people want to go CO, which, as we just mentioned, is cobalt and not copper. Fluorine, definitely one. That is gold. Definitely pops up a lot. AU is gold. Helium, He, hydrogen, iodine, Iron, which is Fe, definitely pops up a lot. This one does as well. That's lead. Pb is lead. Lithium, magnesium, and manganese also, again, does pop up a lot. By the way, argon does as well. That's a noble gas as well. By the way, Sn is tin, so that also does pop up a lot along the way. Definitely mercury, neon, nickel. So, this is a pretty good list of ones that if you have a pretty good familiarity, these tables here, you'll probably be in pretty good shape for most of it. Oxygen, phosphorus, platinum occasionally, potassium, silver definitely pops up, sodium, which is Na, strontium, sulfur, like I said before, tin, and definitely zinc and uranium. And of course, Se, which is my favorite element, which is selenium, that it pops up occasionally as well, right there next to bromine on the list. So as I mentioned before, you are responsible, obviously, for the symbols and the names, and probably practical application of this is going to be when we get into the next chapter and talk about naming. Again, it's just going to help you to understand what the symbols are. That we can focus on kind of the rules that you have to follow when we talk about naming things and stuff like that. Any questions on there? As you can see here, again, some of the origins of these names. Some are Latin name, which is aurum, which is where Au comes from for gold. Silver as well. That is, again, the root of where we get kind of that A and G coming from. All right, so correct formulas here. Iodine is yeah. Iron is, it is Fe. Magnesium is Mg, again, capital M, lowercase g. Zinc is Zn is zinc, and lithium is Li, yeah. They agree. And P is phosphorus, yeah, so P is phosphorus here. Ar is argon, yep, is a noble gas, so that does pop up a lot. Mn is manganese, not magnesium, so that's manganese. Be is beryllium, and K again is our potassium, right? So there we go. All right, any questions on elements, symbols, names? Then let's talk about the structured atom. As I mentioned, we're not going to go into a lot of detail on a lot of these sort of experiments. We're going to touch upon some of the major sort of findings that helped us really understand the structure of the atom. So let's get into some of that. As I mentioned before, all elements listed on the periodic table are really made up of atoms. And atoms, again, are really the smallest sort of version of an element that can sort of do something, come in chemical combination, or have characteristics of that particular element. Now, there was a lot of sort of work early on about atoms, and really one of the major sort of steps to understanding sort of atoms and how they work in a sense came about with John Dalton. John Dalton did Dalton's Atomic Theory, and he developed an atomic theory that atoms were responsible for combination of elements and compounds. Now, one of the things about a theory that we talked about, I think at the very beginning, is the idea that it may not be correct in all aspects of it, and further investigation may prove that some aspects of a theory maybe don't hold up. And with Dalton's atomic theory, that is true as well. There are certain parts of it that over time, based on experimentation, was found to be not so true. And there are some parts that are definitely still true. So let's take a look at some of the important aspects of Dalton's atomic theory. He thought that all matter is made up of tiny particles that are atoms. All atoms of a given element are identical to one another, and different atoms of different elements are different from one another. And this first part of it is actually one of the things that was found later on to be incorrect. And it is this part of it, which is all atoms of a given element are identical to one another. So at the time, he did not know of the existence of what are known as isotopes. And isotopes are the same element, but they have different masses. So obviously, if they are the same element and they have different masses, they cannot be identical to each other, right? If they have different masses, the atoms and stuff like that. So that's one part of Dalton's atomic theory that was sort of later proven to be not correct. Atoms of different elements are different from one another, so that is still correct. Atoms of two or more different elements will combine to form a compound. A compound is always made up of the same kind of atom and number of each of those kinds. So, for example, if you have water, no matter where you get your water from, it may cost you more, it may cost you less, depending on where you get your water. It's still two hydrogens and oxygen that are going to combine together basically to make water. So, if it is water, it will always combine in that sort of ratio of two hydrogen atoms to one oxygen atom, or roughly for every 1 gram of hydrogen, you'll have 8 grams of oxygen that will come together in terms of the masses of those different elements. He also said that a chemical reaction involves the rearrangement, separation, and combination of atoms. We never create nor destroy atoms in a chemical reaction, and that is true. So in a chemical reaction, the only thing that happens is basically you break all the bonds of what you started with, and you make new bonds of what you make. The elements never change in a normal chemical reaction. And as we'll talk about, is because it only involves electrons. So the elements will never change. That is why when we take an equation, we have to balance the equation, and we have the same number of elements on each side of the arrow. That means if you started with 4 carbons in a reaction, you should end with 4 carbons in the reaction. It may be attached differently, it may be in a different compound, but you'll never lose any elements along the way. Another sort of idea that was an early idea was the idea of atoms being indestructible. And that also was sort of later disproven a little bit in terms of nuclear reactions. So when you talk about nuclear reactions, which we do not in this class anymore. So when you talk about sort of nuclear reactions, in a nuclear reaction, pretty much that's all you do is basically change one element into something else in that sort of reaction. But in normal chemical reactions, which is basically all we talk about in this class, you never change the element. The element always stays. You never lose the element along the way. Question on those parts there. So by the end of the 1800s, a lot of experiments were done, and it was really believed that although atoms are extremely small, they did contain a subatomic sort of structure, and they did contain subatomic particles. And those 3 particles, as you may be familiar with, atoms contain protons, which are positively charged, neutrons, which have no charge, and electrons, which have a negative charge. So again, although an atom is incredibly small, it does have an internal structure of even smaller parts that basically make them up. And we're going to talk about each of these parts and some of the parts which are maybe more important than others in a sense of what makes it an element and stuff like that. One of the most important fundamental principles of chemistry and how a lot of chemistry works in a sense is a very simple sort of attraction that occurs, and that is what is sometimes referred to as opposites attract. It's actually known as electrostatic attraction. Much like in life, right? If you got 2 negative people near each other, they don't really want to be there. Their pace is a little bit too negative for one another. You got two positive people, that's just too much cheerfulness, right? To be near each other for too long of a time. What do they always say? You want to find somebody that balances you out, right? So opposites attract, right? So your good characteristics, the other person's characteristics, they kind of balance each other out. And the same thing applies in chemistry. And I can't tell you how many sort of interactions that we talk about is really just a basic idea of the positive side of one thing is like attracted to the negative side of another. So that's a really important sort of principle in chemistry, as we can see here. Again, if we have two things that have the same charge, like two positive charges, they are going to run away from each other because they really don't want to be near each other. Same thing as well, if we have two negative charges, they also will try to escape. But if we have opposite charges, they will definitely attract to each other. That is actually a super strong attractive force when you have a positive and negative thing attracted to each other. As we'll talk about when we talk about bonding, that is the basis of what is known as an ionic bond. An ionic bond is actually no sharing of electrons. That unit is just held together by sticking together. Positive and negative sides of those guys come together and they're attracted to each other. And that is what basically holds like something like an ionic compound like sodium chloride together. What holds the sodium and the chloride together is the opposite charges that each of those ions have. It is also a really important sort of idea, as we'll talk about in a later chapter. That is how, for example, things interact with other things and why certain things, for example, might dissolve, why certain things don't dissolve. And if you get things that have similar types of charges, they're able to interact really well with one another. But if you get things that have very different types of charges happening, they're not going to be able to interact really well with one another. That's why ionic compounds, for example, are very soluble and mix really well with water, because water actually has a positive side and a negative side. So it's able to interact well with a positive ion and negative ion. And that's also why water and oil doesn't mix really well, as we'll talk about, because oil pretty much has no charge. So water sitting there with its charges looking to interact that way. Oil is sitting there with like no charge and they're just not going to interact, which is why oil, for example, right, floats on water, right? If you ever see an oil spill, it just floats on water, it doesn't mix or anything like that, because they have no way to interact with each other over the long period of time. Because pretty much most ways that molecules and other molecules interact, or molecules with itself, for example, interacts, is that interaction right there, that kind of positive negative interaction that occurs. Now, in the context of what we're talking about here with the atom, the understanding of that was used a lot in a number of experiments that allowed certain scientists to explore the atom by using, for example, in a lot of these experiments, they would use radioactive particles. And radioactive particles, very common ones, are alpha particles. And those are positively charged radioactive particles, really like the helium nucleus. There's beta particles, which are negatively charged radioactive particles, like an electron. And there are gamma rays, which pretty much has no charge, but is pretty high in energy. And a lot of these experiments that were done to understand the atom, a lot of these scientists use these different sort of particles and the idea of opposites attract to help them sort of take advantage of exploring particles that do have charges. Other things that are sometimes were deployed in these type of experiments were things like electrical fields, right? So if you had an electrical field, which basically has a positive side and a negative side, right? And if I shot a particle at this electrical field and this particle started to sort of bend towards the positive side of the electrical field, what could I figure out the particle has in terms of charge? What type of charge would it have? If it was attracted to the positive side, that guy probably had a negative opposites. Yeah. So if you're exploring some type of particle like an electron, right, you can use something like electrical field and you could help move the electrons one way or the other. If you shot a particle and it kind of like bent towards the negative part of the electrical field, that would mean that that guy is most likely positively charged, right? And if you shot something and it just sailed straight through, didn't go anyway, that would mean it probably had no charge, yeah? So using something like an electrical field in a lot of these experiments, things like a magnetic field, which works kind of the same way, North Pole, South Pole sort of situation. They were able to really explore these different particles like electrons, protons, and neutrons that have these sort of charges. So this is very beneficial when they were doing these experiments uh, to help explore the atom. One of the first sort of major experiments that were done to really look at electrons was one done by J.J. Thomson. And J.J. Thomson used a cathode ray tube, sometimes referred to as a CRT. A CRT tube there, our cathode ray, is basically a tube that shoots negatively charged particles like electrons. And it has a positive side on one end of the tube, a negative side on the other. And that's going to help my negatively charged particles head towards the positive side, right? Away from the negative side of the tube. You could put some type of fluorescent material on there and you could actually see where it hits. You might be familiar with a CRT cathode ray tube. If you ever have or seen an older sort of TV, like I know they used to be on the ground, right? You call a TV repairman to fix your picture tube. Any type of TV that has a back, not like a flat screen or anything like that. Those guys that had picture tubes in it, those were cathode ray tubes. Older computer monitors that had like the big back that comes out of it, those are also the CRT monitors, or sometimes referred to as your cathode ray tubes. I know you used to, again, call a repairman to fix your TV. You wouldn't just go to Costco and buy a new one and try to fit it into your car, right? When it breaks and stuff like that. We've all seen everybody at Costco. Just take the box away. We'll just throw the TV in there. It's not going to fit, right? It's always the person that has like the smallest car and they come out with the biggest TV. Hey, it's Super Bowl times. Sometimes you need that big TV, right? Strap it to the top and it'll be okay. But the CRT tube was used to explore really the electron. And what Thomson was able to basically figure out from that was the charge to mass of an electron. So he's able to figure out the charge to mass of an electron. Another really important experiment was one done by a guy named Milligan. He did what is known as the oil drop experiment. And what he did is, again, he took advantage of an electrical field. So he had like an electrical field. He shot in some oil droplets and had like a little hole. And the oil droplets would start to drop just by obviously gravity. And what he was able to do was he was able to adjust the electrical field in such a way that the oil droplets would actually just be suspended there. And as they were dropping, they would gain a charge. He was able to kind of adjust the electrical field that the oil droplets will basically just hang there. What that was able to basically determine from that experiment was he was able to determine the charge on an electron. So these two experiments were really important in terms of an electron. Milligan was able to do the charge to mass of an electron. Thomson was able to do the charge to mass of an electron. Milligan was able to figure out the charge of an electron. From both of those information, the mass of an electron was able to be basically determined. And it's on the ballpark of 909 times 10 to the minus 28 grams. I'll go off the top of my head. Hope for the best there. And that's a really small number. Yeah, it's like 27 places to the left, put some zeros and stuff like that, right? A really, really small number. Now, at this time, after these two experiments, it was definitely believed that the atom was neutral. And it meant that obviously the atom had no overall charge and it was neutral. And obviously the discovery sort of electrons and sort of the properties of electrons was really important because obviously then the atom must have some type of positive part to it to balance out the negative charge of the electrons. So one of the earliest sort of models of the atom was the one that's referred to as the Plum Pudding model of the atom, which is shown on the bottom here. And basically the idea was that that positive charge that was necessary to balance out those negatively charged electrons was found really just spread out all over the sphere here. And that idea there is like that's the pudding. And the electrons were embedded inside. That's like the raisins in the pudding, in case you've ever had it. And that was basically what the early model of the atom was. You have this big sphere of positive charge all spread out. You have these like kind of electrons embedded inside the atom. And it was also believed that most of the mass of the atom was made up of the electron. So this is, again, really an early model of the atom and sort of an accepted model of the atom. But like most things, research and experimentation continued. And the next major sort of step towards really understanding the atom came with Rutherford and the Gold Foil Experiment. This was a really major experiment that was done that really sort of changed how we view what the atom looks like. So again, going into this, Rutherford and everybody believed, like we just saw there, that basically the atom is all this positive charge spread out. And again, embedded inside here are some of these negatively charged electrons. So what Rutherford did was he took alpha particles, and if you remember, those are our positively charged particles, and he basically shot them at pieces of gold foil, which are basically atoms of gold, basically. And what he expected to happen was when he shot these positively charged particles, which are moving really, really fast, he expected it to go through, but there would be some deflection, right? And again, that's because we're shooting something positive at like a putting a positive sort of charge all spread out over it. So if you think about like the atom, and this is the plum pudding model, the entire paper is like the positive charge, right? And if I held one end and somebody else held the other end really tight and we shot like a pin at it, right, really hard, it would be able to probably come through, right? But as it would come through, it would probably deflect a little bit as it tried to bounce through there. And that's really what they expected to happen. So they expected to shoot these things and, it would be able to pop through all that positive charge because the positive charge is really spread out over the entire atom. These alpha particles are moving really fast and they're heavy. So they're able to kind of pop through and come to the other side. They were actually really, really surprised when they did the experiment. When they did this experiment, what they saw was they saw that most of the alpha particles went right through, undeflected. But what they also saw was every now and then, an alpha particle did scatter at a large angle. And sometimes it even like came right back to the source it was shot at. So as you can see here, this is the setup. This is our alpha particles coming in. This is just a little deflection or detector ring. And that's our atom of gold. And what they saw was, again, most of them just sailed right through, no problem. But they did see every so often, we got some bouncing off at these sort of larger angles. Some would even come back to the source. So this was very surprising based on the plum pudding model where they expected everybody to go through with some deflection as it's going through this nice little pudding of positive charge. So what that meant was a couple of things. If they shot these alpha particles and it went through undeflected, what did it hit? Well, if I took my pen, which I won't do and throw it, but if I threw my pen that way, right? My pen is going to just go on through, right? It's not going to hit anything. There's nothing in its way, right? And that's what they basically discovered was all these particles that just sailed right through had to hit nothing, right? But we also had a lot of particles that scattered at really large angles. So those particles did have to hit something. And if those alpha particles were positively charged, What type of charge thing would make it bounce off at a really large angle if it hit it? Yeah, it had to hit something that was very, very, very positively charged, very densely positive charge to make that really heavy alpha particle that's traveling really fast just jump out at the opposite angles and move really fast away from and be deflected. So, what they really determined from this was basically they had to kind of go back to the plum pudding model, put an X over it, and go, that's not so correct based on really our experiment that we did. And basically, what they said was the atom was basically empty space. And that is why they can account for those particles just sailing through with no problem, because frankly, they didn't hit anything. So nothing got in its way. They just sailed right through. It also had a very dense positive core, which they call a nucleus. And that core was later found to contain our protons, which are positively charged. And not at this time, but in about 1930s, it was also found that neutrons, which have no charge, are also found in the nucleus. So both protons, which are positively charged, are concentrated in this nucleus, which is why it's very, very dense and made the alpha particles bounce off at these large angles. And in the 30s, it was later believed and sort of proven by a guy named Chadwick that neutrons actually existed that have no charge, and they're also in the nucleus. The other major difference between the plum pudding model and really the modern version of the atom, which is the current version of the atom, is that most of the mass of the atom is actually the nucleus. So the nucleus, not the electrons, actually account for most of the mass of the actual atom. Any questions on that there? So as I mentioned before, the nucleus has the neutrons and protons. And again, neutrons have no charge, protons have a positive charge, and electrons are out and about. So really our version of the atom is here we have our protons, which are positively charged. We have our neutrons, which have no charge in our nucleus. And the electrons are out in that empty space from the nucleus. Is there going to be an attractive force between the electrons that are flying around and the nucleus? Should there be any type of attraction? The electrons are negatively charged. The nucleus is overall positively charged. So there is an attraction between these two, right? There is an attraction between those two. That's why electrons just don't fly away, right? They're actually tied to the nucleus through that attraction. Some are tied a lot tighter to the nucleus, held tighter to the nucleus than others. And as we'll talk about in bonding, that's why only certain electrons are involved in bonding. Other ones are just too close to the nucleus and really kind of locked into the nucleus. They can't really escape. By the way, just so you know, electrons do not travel in orbits. They do not travel in pretty circles, even if biology tells you. They do travel randomly about the nucleus. So they do travel in a random pattern around that empty space. There is something that is known as the Heisenberg uncertainty principle. And that basically says if you take a particle like an electron, the more you know about how it's traveling, the less you know about its actual location. So we don't know exactly how an electron travels. It travels randomly about the nucleus and in that empty space, outside of the nucleus, obviously in that empty space. But what we think about in terms of where electrons are and stuff like that, they do not travel in pretty circles and orbits or anything like that. But we think of it as more of a probability, like, hey, in this area of the atom, there's like a higher probability that you might find an electron. Not really sure how it got there, not really sure how it's moving, but there should be a pretty good probability. And in other parts, there's going to be a lower probability of finding an electron. Clearly, the highest probability of finding an electron, again, not really knowing how it's traveling, how it's moving, should be near the nucleus with that positive charge, right? There should be a pretty good high probability of negatively charged electrons in that area. As you move away from the nucleus, the probability gets lower. Doesn't mean you can't find electrons further away from the nucleus. It just means there's probably a lower probability of finding it. Any questions on that there? Now, a mass of the atom and the way that we sometimes weigh something is what is referred to as atomic mass units, or AMU. And much like a lot of things in chemistry, where we cannot sort of directly measure something. So, for example, atoms are extremely small. You can't just pick up one atom of an element and just like drop it on a scale and weigh it. So, in that situation, a lot of times what we do is we pick something to use as a standard. And the thing that we use as a standard is a carbon 12 atom. Is the standard that is used. It has a mass of exactly 12 AMU. Also has 6 protons and 6 neutrons. And basically what they did is they go, well, hydrogen's only like, 1/8, 1.8% as big as a carbon 12. And they do like a little math to figure out what the atomic mass is of it. Now they've done that for protons and neutrons. The mass of those guys in AMU is 1.007 for a proton, 1.008 for a neutron, and the mass of our electron is 0.0055. Those are our 3 subatomic particles. Which one is the heaviest? It is the neutron, just barely. It's the heaviest of all 3 particles. The lightest is actually the electron. Both the proton and the neutron, each individually, are about 1,850 times heavier than any electron that's flying around. This also sort of reinforces the idea of Rutherford's model of the atom, that most of the mass of the atom is made up of the nucleus. Because again, in the nucleus, you have protons, you have neutrons, which each are 1,800 times or so heavier than any electron that's flying around. So most of the mass of the atom is made up of that nucleus, which has those heaviest particles, both protons and neutrons. And unlike the Plum Pudding model, not the electrons. Any questions on that there? By the way, we'll talk about a little bit later on in this chapter, but if you look on the periodic table, that is what you see on the bottom. The atomic mass of each of those elements is that number that's on the bottom of the symbol. So here we go. That is, again, what our nucleus looks like. Pretty much all elements will have protons, electrons, and neutrons. The one exception is hydrogen. Hydrogen only has a proton and an electron. It does not have a neutron. So everybody else has protons, electrons, and neutrons, except for hydrogen, which has a proton, an electron, and no neutrons. All right, so let's take a look at this. Which of the following subatomic particles fit the descriptions? The one that is found outside the nucleus is? It is the electron. Again, they're flying around that empty space in a random pattern. The one that has a positive charge is proton. And the one that has no charge is a neutron. Yeah. Again, these 2 guys in the nucleus, this guy flying around outside of it in that empty space. Yeah. True or false? The mass of an electron is greater than a proton. Which one's the heaviest? Proton, electron, neutron? Close. It is the neutron, just barely edges out the proton. They're very close, but the neutron's actually the heaviest, which makes actually the electron the lightest of all those. So that should be false, right? Protons have a positive charge. Electrons have a negative charge. That is true. Nucleus of an atom contains only protons and neutrons. That is true as well. Yeah. Question on those there. So when you think about the atom, this is sort of really what the atom looks like. You could think of the atom like the Superdome, for example, like big football field, and like the nucleus is a small little marble on the 50-yard line, right? If you ever been to the Superdome, very scary seats. Even when you're sitting in your seats, you feel like you're falling because it's so big. But again, like a big football field on the 50-yard line, it's kind of like the nucleus. All the rest of the football stadium is basically the empty space where those electrons are basically flying around. And again, most of the mass is going to make up of that nucleus, which has our protons and neutrons. By the way, we were talking about sort of electrons do not travel in pretty circles. This sort of bluish thing, which I think you could not really see very well up there, but there is some different shade of blue sort of happening here. And this is what is sometimes referred to as an electron density map. And again, in that sort of darker area, which when you look at maybe the video later or your notes, is kind of closer to the nucleus. And that lighter blue sort of gets lighter as you move away. And again, a lower probability of finding electrons. But basically, our electrons in this empty spot sort of moving around randomly about the nucleus. Any questions on the atom? So you need to know some of those experiments, and obviously you need to know early model of the atom, the Plum Pudding model. You need to know what was wrong with it after Rutherford's experiment, and obviously the current model of the atom. You need to know where protons, electrons, and neutrons are found. You need to know which one's the heaviest, the lightest, and you need to know their charge. Any questions on any of that? Okay. So continuing on with atoms here, we're going to talk about some important aspects of atoms, and that is atomic number, mass number, and isotopes. So the chemistry of atoms do come basically from electrons. So in basic chemical reactions, which again is what we deal with in this class, it's all about electrons. So if you think about how the atom is set up, as we just talked about, you pretty much have electrons flying around on the outside, which means when two atoms come together, it is the electrons that say hello to each other first, right? They're the ones that come in contact with each other. So again, in basic chemical reactions, it's all about electrons. It has nothing to do with what's in the nucleus. The only ones that do deal with what's in the nucleus is actually nuclear reactions deal with what's inside there. But in basic chemical reactions like what we deal with, it's all about electrons. And electrons are really all about bonds as well, and making and breaking bonds. So let's talk a little about some of the important aspects of an atom. The first one is the atomic number. The atomic number is sometimes abbreviated as a Z. And the definition of atomic number is the number of protons that you have in an atom of a particular element. Now, if you have a neutral atom, and as we talked about, there's only 3 particles inside an atom. There are protons that are positively charged, there are electrons that are negatively charged, and there are neutrons that have no charge. If an atom is neutral, that would mean that the atomic number will also tell you the number of protons, but will also tell you the number of negative electrons. So if we have a neutral atom, all the positive protons need to be balanced out by all the negative electrons. And it is important, though, that if you are asked a question of what is the actual definition of atomic number, the actual definition of an atomic number is only the number of protons. So it tells you only the number of protons. The sort of side note that you could get from that is if it is neutral, it will also tell you the number of electrons. But again, if you're asked a basic question of give me the definition of atomic number, it should only be the number of protons. So that is the actual definition of atomic number. The atomic number can be found on the periodic table. If you look at a periodic table and you find like your friend hydrogen and you look at the number up on top, that is the atomic number. You look on the periodic table, find your friend nitrogen right there, atomic number. Carbon, 36, right there up on top. So the atomic number is found on the periodic table. It is the number that's above the symbol. If you look at that periodic table or any periodic table you have maybe at your seat, do any of the top numbers repeat? They do not. Every top number is different. That means every element has its own unique atomic number. That also means that when we talk about protons, electrons, and neutrons, which particle is the most important in terms of what element you're dealing with? Definition of atomic number is the number of, and since every element has a different atomic number, the most important of those three particles are protons. The protons is what determines what element you are dealing with. That is also why when you do a normal chemical reaction that only involves electrons, you never touch the protons. That's why we never change the elements, because we never do anything that involves protons. So we always have the same number of protons, although the electrons may move. The number of protons stay the same, so it's the same element. So you can basically determine what element you're talking about if you know the number of protons, or you know the atomic number, which is basically the exact same thing. You'll know exactly what element you're talking about by just simply going to the periodic table and finding that number. Or if you know the element you're talking about and you want to know how many protons it has, you would then go to the periodic table, find its symbol, and look at its atomic number, and you would know how many protons it has by that. So the periodic table is your friend when you're doing that. So if we look at nitrogen, as we see there, when we go to the periodic table, we can find its atomic number. That means if I have a neutral nitrogen atom and it's neutral, it has nothing written there at the top right, it has no charge, has no positive or negative there. That means that my nitrogen atom here would have, in terms of protons, 7 positive protons. And to balance it out, it would have 7 negative electrons because it has no charge, right? 7 positive guys plus 7 negative guys give you no charge overall. And again, that was what a nitrogen would have. Would I ever have a nitrogen atom that has 6 protons? I would not, because the one that has 6 protons is carbon. Yeah. So it would be carbon and stuff like that. So again, protons really important. It tells you basically what element it is. You can use the periodic table to figure out the element if you know the number of protons, or if you know the element, you can use the periodic table to figure out how many protons it has. Any question on that one there? The other important number is the mass number. The mass number is abbreviated with an A. The mass number is the number of protons and neutrons there are in an atom. And the mass number is important because if you take the mass number, which is A, which is our number of protons plus our number of neutrons, you take our atomic number we just talked about, which is Z, which is the number of protons, and I subtract those two, what cancels? Tells you the number of neutrons. So to figure out the number of neutrons that something has, you would take the mass number minus the atomic number, and that will tell you the number of neutrons. Vice versa, if they give you the number of neutrons and you know the number of protons, you add them together, and that will give you your mass number if you need it. When you calculate all of these things, a really important thing to remember is this. If you calculate the mass number, if you calculate the atomic number, if you calculate the number of protons, electrons, or neutrons that somebody has, they all should be positive whole numbers. Yeah. So you should always have positive whole numbers. You can't have like a half a proton hanging out, or a half a neutron, a quarter of a neutron, whatever it may be. So that brings up the question of, if I go to my favorite periodic table, whichever one that might be for you, and I look at a lot of numbers that are there, are these numbers on the bottom the mass number? I see yes and I see no. So one of those is the right answer, I'm assuming, unless they're both right. They're not both right, by the way. What did I just say about when you calculate mass number, atomic number, protons, electrons, neutrons, they need to be what type of number? Are the things that I just circled whole numbers? They're not. If you look at the periodic table, pretty much all the numbers on the bottom are not whole numbers. These are not the mass numbers. These are what we'll talk about a little later on in this chapter, the atomic mass. What confuses people is this. A lot of times the atomic mass that you see on the periodic table is sometimes very close to the mass number in certain elements or isotopes. So what people commonly think is, oh, they must have just like rounded to get that number, basically. And that's not the case. So do not ever on a test or something use the number on the bottom for the mass number, or if you do, just cross it out yourself, save my pen some time, yes, and don't do that. So that's a really good way to remember. If you find yourself writing decimals for a mass number, it's wrong for sure, yeah. And again, it's not from that number on the bottom. It's not like the rounded version of that number. The way that you'll be able to figure out the mass number or the number of neutrons is you'll be given enough information in the actual problem to be able to calculate the mass number or be able to calculate the neutrons and stuff like that. So you'll be given, for example, like I said before, you may be given the number of protons and the number of neutrons. And in that case, you just need to add them together to get the mass number. You may be given the mass number and know the number of protons, which you could then subtract and get the number of neutrons from. So in the actual problem itself, it'll give you enough information to really calculate all three of those things, the protons, electrons, and neutrons. The only thing that may not be given to you in the problem is protons, because you don't need it. You just need to know the element, right? You could go to the periodic table and figure out the protons. So out of those two things, mass number and atomic number, it is only the atomic number that you can find on the periodic table. Once again, the number on the bottom is not the mass number. And again, it does need to be whole numbers. Any questions? Now, isotopes are, as I mentioned before, the same element, but they have different masses. The reason they have different masses is because they have different numbers of neutrons. As we just talked about, they cannot have different numbers of protons. Otherwise, they would not be the same element, right? Because protons got to be the same. As I mentioned as well before, everybody will have protons, electrons, and neutrons except for hydrogen, which again only has a proton and electron. It has no neutrons. You can write the symbols with the mass number and atomic number like so. You use the symbol top left mass number, bottom left atomic number. So if we look at this, which is example of some isotopes, hydrogen has one proton, no neutron. Deuterium, which is actually heavy hydrogen, has one proton, one neutron. Tritium is the radioactive version of hydrogen, has one proton and two neutrons. So if we were going to write the symbol, this is what we would want to do. We would want to look at this, and it says it has one proton. So if I did not know that, I should go to the periodic table and look at for number 1, and I will see the symbol H, right, which is hydrogen. And that is the symbol I should write. Bottom left should go the atomic number, which is the number of protons that we could get from the periodic table. So that is our atomic number. The mass number is the protons and neutrons added together. So for hydrogen, that is 1 plus 0, which is 1, and that would go up on top, which would be my mass number. Yeah. And that would be the correct way to write the symbol for the isotope of hydrogen. Generally speaking, if it is written like this, to find the number of neutrons, top number minus bottom number, right? 1 minus 1 is 0, number of neutrons. So top number minus bottom number will give you the number of neutrons. Now, when you get to this guy, which is deuterium, doesn't sound anything like hydrogen. But what we do know is it has one proton, which means if I go to periodic table, that is still hydrogen because it has only one proton, even though it has a different name. And we would still use the same symbol for that guy because it has one proton and it has the same atomic number. In the case of deuterium, one proton, one neutron gives me a mass number of 2, which goes up on top. Again, if you take the top number there, 2 minus 1 gives you 1 neutron that deuterium has. Once again, tritium doesn't sound anything like hydrogen, but I know it's hydrogen because, again, I see 1 proton, which means it has to be atomic number 1, which is hydrogen. So we would still use hydrogen symbol, and it still has 1 proton, which means it has an atomic number of 1. And in this case, 1 plus 2 is 3. It would have a 3 on top. Again, top number minus bottom number, mass number minus atomic number, 3 minus 1 is 2 neutrons. So this would be the symbol for hydrogen. This would be the symbol for its isotope deuterium. And this would be a symbol for the other isotope, which is tritium. They are all hydrogen, even though they have different names. And they are all hydrogen because they all contain 1 proton, right? Again, the proton being the most important thing here. Question on that there. Now, sometimes isotopes are written like this, say copper 64. So the 64, is that the atomic number? Is that the mass number? By the way, if I go to the periodic table, this is what I see for copper. No, I don't. I see 29, maybe. That's what I see there. It's kind of like a 6, but not so right. There you go. Oh, you see a 29 there. That means the atomic number for copper is what? So on the periodic table, that's what copper's little square looks like. What would the atomic number be for copper? The atomic number is the number of protons. It is the top number. Yes, did you find on the periodic table? That's the atomic number, right? So the atomic number for copper is actually 29, which means the 64 cannot be the atomic number, right? So it has to be the mass number. So that's a very common way that they're also written. Symbol dash a number, that number is the mass number. That would mean in this case, how many protons would copper have? Would have 29. And this is neutral, which means how many electrons would it have? Have 29. That's 29 positives and 29 negatives. How many neutrons would it have? Neutrons, I don't know either. The 64, which is the mass number, minus our atomic number. Feels like a lot at this time. What'd you say there? 35? It sounds like a good number. We'll go with that. Why not? We'll try it without the calculator. We'll go with 35. I think it's right. Any questions on that there? So again, that's a very common way that isotopes are sometimes written. All right, why don't you try some here? For each of these guys, we're looking for how many protons, electrons, and neutrons does each of these have? So take a moment and see what you come up with. Okay, so let's take a look. Once again, we're going to look for protons, electrons, and neutrons here. First off, our top number, as we've been talking about, is our mass number, right? Which is our number of protons plus our number of neutrons. Our bottom number is our atomic number, which is our number of protons. We also know that this thing does not have a charge because there is, again, nothing written there. If it did, you'll see like a plus or a minus written there. Actually, none of these guys here have anything written there. So we could safely assume that in each of these cases, it is neutral. Again, if there was a charge, something would be written there. Maybe next time we'll talk about what happens if something does have a charge and what you have to sort of do. So in this case here, CO, by the way, is the element. It's actually cobalt, right? So that is CO, which is cobalt. The number of protons we could get simply by looking at the atomic number, right, that we could find on the periodic table. And that would mean in this case, we have 27 positive protons, right? Because this guy is neutral, that would mean how many negatively charged electrons should we have? We should have an equal number of negatively charged electrons. That gives us a grand total of 0 for the charge, which is again why it is neutral in this case. Now, to find our number of neutrons, remember that you could take the mass number minus the atomic number, which in this case is basically the top number minus the bottom number. And that will get you 60 minus 27 in this case, 33. It's just too hard to pick up the calculator, but I'll go with 33. Sounds good. 33 neutrons. Any questions on that one there? Look at the next one, which is Cl. Cl is fluorine, right? And again, no charge. So starting with our atomic number, which is the bottom, we now know that it should have here 17 protons. Because again, it is neutral and has no charge, we need an equal number of electrons, as that is really the only other thing that has a charge in the atom, which will give us 0 in terms of our overall charge. And once again here, we could take our mass number, which is on top, and our atomic number, which is on the bottom, to get our number of neutrons, which I scribbled, but I think it's 37 minus 17. I'll go with a 20 on that one there. Any questions on that there? Again, you can see each of those numbers are whole numbers. I did not go to the periodic table other than maybe to look at the atomic number. But everything else, again, should obviously be whole numbers. Lastly, U is uranium. And coming down here to our atomic number, which is 92. So that is how many protons we have, which is the definition. Again, it being neutral means we're going to go equal number of electrons to give us no charge. And our number of neutrons in this case, 238 minus 92 gets you a lot, like a $1.46. Yeah. There. And that will be our number of neutrons. Any questions on any of those? So again, as I was talking about before, you can see here, you really will be given in these separate problems enough information to be able to calculate protons, electrons, and neutrons, or mass numbers. Again, really, again, the only thing that you should be going to the periodic table for should only be the atomic number or the number of protons. Any questions on that? All right, well, I need a nap, so we're gonna call